Welcome to the course. I hope the midterm has made you all very happy. Yes?
We will have the points about the midterms before the exam, after?
You will have them before the Christmas vacation.
Thank you.
That's all I can guarantee. That you will eventually have them before the Christmas vacation. Yeah? But not after. So before the blockus, you will have them, for sure. That's all I can guarantee. Unfortunately, I'm busy and I can't always do what I want, you know. It's tough, life of professor and being so busy. So today I want to talk about two things. First, I want to finish Causal Reliable Broadcast. So last time we saw this correct but very non-optimal version called fail silent no waiting. Today I want to show you the code for how to garbage collect it. And the interesting about garbage collection in general is it needs P. Garbage collection is tough. It needs perfect failure detector. And then I'll show you a version that does not have this passed list. It's much more efficient, called fail silent waiting. It uses a vector clock. Vector clock, very nice idea. I finished by talking about all the different broadcast algorithms. There's so many of them, so I will explain that. And then I will talk about the heart of distributed systems, which is consensus. This is the heavy-duty gorilla that does most of the hard work in today's existing distributed systems. So I'll define it with the properties. Also, uniform consensus. So remember we had this uniform reliable broadcast compared to regular reliable broadcast. So you remember what it means. Uniform means that if something happens for a failed node, then it has to happen for all correct nodes. And it's the same for the consensus. Consensus has to make a decision. So the broadcast will deliver, but consensus has to make a decision. So if the failed node is able to decide before it fails, then all the correct nodes have to decide the same thing. So there's also, uniform is also for consensus. So it's the same idea as uniform for reliable. And I'll show you an implementation called hierarchical consensus. This one is pretty simple, but it's not the best one. Then we will search for the best one. We will search for how to do consensus with an eventually perfect failure detector. And this is a tricky business. Okay. So let me start by talking about causal reliable broadcast. So I refresh very quickly what we saw last time. So the interface. So let me go quickly to the interface. So reliable causal broadcast, it's a regular reliable broadcast with this CB property added. And we'll build it layer. We'll layer it on top of reliable broadcast. If a node delivers M, then it must deliver every message causally preceding. Okay, so we saw that last time. And for uniform, it's only the UR, this changes. So the CB is the same. So actually, the uniform and the non-uniform, we don't have to do anything different here. We're in luck for once. The uniform does not make things more complicated. So the trick is, in the first algorithm, is that we keep track of all causally preceding messages. Okay, we have every node has a list, ordered list called past M. So which is, when you put it in the message, it's past M. So each message, when it arrives, it has a list of all the causally preceding messages. And then the node that receives can fix things by delivering all the messages that were not yet delivered. Okay, so we made some examples of this. So I will not go over them again. So we saw the code. Let me go now just this code, and I'll stay for a minute on this code because I want to add garbage collection to this. So today we want to implement a kind of garbage collection. So remember how it works. So the causal reliable broadcast does a reliable broadcast, and then when you do reliable deliver, you have to do all kinds of stuff. So first of all, you check for no duplicates. Then you look at the past M list. All the messages in the past of M, if they're not delivered, so N is in the past, then you deliver it, and you add it, and you append it to the past of that local node. So you do this first, then you deliver M, and then you add M to deliver it and add it to the past. So this is the algorithm. So you see, it's very intuitive, huh? Okay, so we proved the correctness. I'm not going to do that again. The problem with this algorithm is that this past M list gets bigger and bigger and bigger all the time. So we can get rid of that by doing a garbage collection. Okay, so there's many, many, many ways of doing garbage collection. If you run Java, you will have garbage collection. If you run Erlang, you have garbage collection. So we're not talking about that. We're doing a form of distributed garbage collection here. Okay, so how does that work? So when all correct nodes got the message M, then you do not need to keep it in the past list anymore. Okay, so you determine when all correct nodes got the message M. Notice correct node. You don't care about the failed nodes. So you need a perfect failure detector. So that's a pain, huh? In fact, garbage collection in general is very hard in a distributed system. And usually if you really want to do it well, you'll need a perfect failure detector. Okay, so let me show you code for garbage collection. Okay, so this code, you add it to the code I showed before. So you have some extra initialization. You have this ACK array now. For each message, M, you check to see who got it. Okay? And so all nodes that got it will send acknowledgement back to you. You will have also this crash handler. So you manage this correct variable. So it's a set of all correct nodes. And then you have here an extra piece of code and another extra piece of code. Okay? So this extra piece of code will broadcast the ACK. Okay? So when you have an M that's delivered, so notice the condition here is just Boolean, huh? There's no message here, huh? So this Boolean condition is checked after everything. So when a message is actually delivered from the previous code, so when it's delivered, and I have not yet sent acknowledgement, then I will add self. So that's the process node itself, the ID itself, to ACK-M. So this is like duplicate detection, huh? So that I only do one reliable broadcast. So you see, whenever I deliver a message, I will do a broadcast, and I will tell everybody, I got it, okay? And then everybody receives the RB deliver here, and adds the PI to the ACK-M. So notice this ACK-M is kind of a very sophisticated array. Huh? It's dynamic, and it's indexed by a message. A message can be complicated record, of course. Huh? So this is actually a sophisticated data structure, you can see, if you want to implement this. But in our pseudocode, we're assuming that anything sophisticated exists. Okay, it makes the code simple. So we add PI, so this is the guy who got the Emma to ACK-M. And then we have this Boolean condition. If correct is a subset of ACK-M. So the way I read this is if all correct nodes acknowledge M. So the way to read this kind of Boolean expression is that all correct nodes got M. If that's true, then I don't need to have M anymore in the past list. Huh? So I have this function remove, which I don't define. Again, pseudocode, I'm assuming, exists. The message M with any node that it's coming from, I remove M from the past list. Okay, so this is the garbage collection. See how it works? So the code is very simple because I'm assuming very nice operations here. So if all correct nodes have gotten M, I don't need it in the passed list anymore. So the passed lists, they're going to keep shrinking. As the nodes are getting M, these passed lists will always be shrinking. And this code runs concurrently with the regular algorithm. So the garbage collector is always running. It's always running at the same time as the regular algorithm is running, and it's doing its best to make the passed list smaller. So the algorithm is running normally and the past is growing, and then this guy is running in parallel with the other one and making the past list smaller. You see that? So this code is just added to the previous code. So the previous code, you don't even need to change it. Okay? So this is a one-page garbage collector. The problem with this garbage collector is it needs a perfect failure detector. Okay? But there's some other little questions that we can ask about this garbage collector. Now, I'm garbage collecting the past array. Now, a smart student will notice that the ACK array is also growing. So it's like we're reducing the past array, but we're not getting anywhere because we're also growing ACK. Okay, so I've actually kind of left that out on purpose. You can use the same, almost the same code. Of course, you can also garbage collect the ACK array, yeah? So how do you do that? How would you do that? When can you remove? So ACK-M is a set of nodes, Yeah?
You only keep track of X of messages that are not yet removed. If a message is removed, then you don't need to...
Yeah, so if this condition is true, then you don't need ACK-M anymore after that. So here you can also remove the part ACK-M. You can basically reset it, remove it. So ACK-M is a set. So this is like a hash table, ACK-M, where it's indexed by this data structure, but you can remove an entry. After this condition is true, you don't need ACK-M anymore. Okay? And then you can remove it. And then we're good. Now we have that real garbage collector. So I let you, as an exercise, add the code for that. Okay? Okay? So that's the first question. I have a second question now. So we used a perfect failure detector in the garbage collector. What happens if we use an eventually perfect failure detector? Remember, that's a big theme of the course. We do first an algorithm with P, but since internet is eventually P, we have to figure out how to do it with eventually P. So the question is very natural. What happens to this garbage collector if instead of a P, we use eventually P? First question is, does it still work? Sometimes we get lucky, sometimes we're not lucky. What happens in this case? What happens here? Yeah?
Eventually, P might detect that a node crashed, but it doesn't crash.
Right?
So when we deliver, it's not included in the correct set.
Right?
So we don't check if the node acknowledged the message.
So so what happens then? What is the conclusion?
The node might not acknowledge the message, and we still remove it from the past.
The node might not acknowledge the message, and we still remove it from the past. Exactly. So the correct set might be too small, because the eventually perfect can make mistakes. It might think many nodes are crashed, even when they're not. So this correct set might get very small, so we might think that all the correct nodes acknowledged, but it's not true. And the result is that we remove too many M's from the past, and that means the whole broadcast algorithm is incorrect. It's buggy. So if we change P by eventually P, the whole thing becomes buggy. Doesn't work. That's too bad. We're not lucky in this case, huh? Actually, garbage collection is a tough problem. In realistic, it's really not known how you can do really garbage collection in an eventually perfect setting. So how do real systems do it? Well, they usually have rules of thumb. So for example, Java has what's called a lease mechanism. So if I have reference to remote object from another node, then if there's no more remote references, then I can garbage collect that object, right? So how do I know that? Okay, that's not so easy. So the way Java works, there's a lease mechanism. Every remote node to an object sends a message regularly to the owner of the object saying, I need that object for at least 1 more hour. And so the node that owns the object knows it has to keep the object for like an hour. But after the hour is done, if nobody has leased the object again, in French, lease is un bail. Les autres ne, ils louent l'objet. They are renting the object. They're saying, I need it for another hour. I'm paying you. I'm sending you a message. I need it for another hour. But if there's a problem with the network and no lease messages arrive, the object might incorrectly get garbage collected. It might be removed even though somebody needs it. So in real systems, garbage collection is hard and eventually perfect. So this is a problem, and real systems have to, usually it's the programmer's responsibility. So it's all pushed up to the programmer level. Okay, so that's enough about garbage collection for now. So you should think a little bit about that. Let me now show you another implementation that does not have this huge past list, that does not need this garbage collection. So in some sense it's better, but it might be a little bit slower. The messages might arrive a little bit slower, and I'll show you why. So there's like a trade-off, huh? So remember, in the first algorithm, every message sent a history of all the causally preceding messages, okay? But we can actually do something a little bit more clever than that. We don't actually have to send all the messages. We just have to send how many preceding messages there are. Okay, so a message arrives at a node and it says there's 5 messages before me and the node only got 3, then it knows it has to wait for 2 more. You see that? There's a gap. If the process got 3 messages and the message arrives and it says, I have 5 in my past, and it says, oh, I only got 3. So that means it has to wait for 2 more messages before it actually can deliver. You see how that works? There's a gap, and you have to wait then. This is why it's called a waiting algorithm. But of course, it has to be done for every process. So in fact, it's not enough to send one number. You have to send a vector clock, okay, or vector timestamp. So I'm going to refresh you on that. So the past history is a vector clock value, vector timestamp. So it tells you how many messages are passed from every other process. I'm waiting, I got 3 messages before me on P1, 2 before me on P2, 5 before me on P3, so it's a vector, okay? Because when new messages arrive, you have to make, depends on where they're, which PI they're coming from. You can't just use one number or it's not correct. Okay, so we're going to use vector clocks. So remember the original vector clock we defined. It actually updates vectors for every single event on the execution. But here we're going to do that a little bit differently, because we're not interested in all the events. We're only interested in how many broadcasts there were. So all the little events of the algorithm We're not interested in that. We're only interested in how many broadcasts. So we're going to have a vector clock that counts. So at node pi, VC of j, so for another pj, it will tell me how many messages that I got from pj that are causally before me from pj. So for every node, and also the node itself, this is how many messages were broadcast on pi itself. So if I have a pi, so let's say I have P1, P2, P3, okay? And I have some broadcasts here. Here's a CO broadcast, CO broadcast, CO broadcast. This is kind of very schematically, yeah? CO broadcast. And I'm here, okay? Then at this point, I have two messages that were broadcast from P1 before me, 3 from P2, and 1 from P3, okay? So it tells me how many messages are causally before me on every process. And that's important because when I do another broadcast, it depends whether or not I have to wait, depends on the process it comes from, okay? Okay, so summarizing, it's a vector clock, but only for relevant events. The original vector clock we defined a few classes ago was all events. So you can see vector clock is a very general idea. You can kind of customize it. And real distributed systems, they will have lots of little custom vector clocks in there. So this is like a custom vector clock. Okay? So the way it works, so the algorithm is very simple. It's actually even a little simpler than the other one. You piggyback the vector clock, not a past list, but the actual value of the local vector clock on the message. And when you receive a message with an attached vector clock, then you have to compare that with the local vector clock. So you have VCM, and then you have a local vector clock. But the local one, there might be less messages. So you have to wait until the local one catches up with VCM. So you only deliver M when the VCM is less than or equal to VCI. So basically it's possible that the VCI is lower than VCM and messages will be arriving, and eventually the VCI will catch up to VCM, and then the gap will be closed. You see? It's a gap. I'll show you some examples. And once the gap is closed, then you're allowed to deliver M. So that's how it works. So let me show you an example of it. So here we have 3 processes. The vector clocks are 0, 0, 0. Here I do a broadcast. M1. The vector clock here becomes 1, 0, 0. But here the messages are not arrived. They have not actually arrived yet. They're on their way. And now this one is delivered here. Okay. Fine. And now it's delivered here. So this one is okay. There's no gap. You see 0, 0, 0, 0, 0, 0. There's the same. So there's no gap, so you can deliver it. Okay. Now I'm doing another one. Now notice when I do M2 here, the vector clock becomes 2, 0, 0. So if I do another broadcast, there's going to be 2 in the past. Okay, and the piggyback, it has 1, 0, 0 on it because there's one guy in the past of M2. 1, 0, 0 and 1, 0, 0. Okay, so they're still traveling. Nobody has arrived yet. Okay, and then first it's delivered at P1. There's no problem there. It's also delivered here. Because here we have 1, 0, 0, which is the local vector clock, and 1, 0, 0, which is the one coming on the message. So there's the same. There's no gap. So we can deliver it. But here we have something. Assume that this message here is very, very slow. This one is faster. So the 1, 0, 0, so the M2 is arriving at the node before M1. So it's arriving at the code of the broadcast algorithm, but it's not delivered to the application. So the broadcast algorithm receives it here, but cannot deliver it yet. Okay? You see that? So it has to hold M2. And the reason is, if you look at 1, 0, 0, and you look at 0, 0, 0. So the 0, 0, 0 is behind. It's lower than 1, 0, 0. There's a gap of one message. It has to go at least, this one has to be at least at this level. Otherwise there's a gap. You see that? There's a gap of one message here. And here there was no gap. 1, 0, 0, 1, 0, 0. Here there's a gap. So we cannot deliver it. So what do? Well, we hold it locally. We have like local data structure. We just keep it, and we'll deliver it later. And then some later time, M1 arrives with 0, 0, 0, and then we can deliver it, because for that one there's no gap. And notice for 0, 0, 0, 0, 0, 0, there's no gap. They're at the same level. So we can deliver M1. And then we increase the clock, the local clock, 1, 0, 0. And now that there's no more gap between these two. So now we're actually allowed to deliver M2, but only then. Okay? So you see how it works with the gaps? So now we can deliver M2. So this gives you an idea, good intuition, right? You see how it works, huh? So now we have to write the code for that. It's not so complicated in lines, this code. Okay. So here's the algorithm. So the first is I initialize. So I have no failure detector. I have a local vector clock. This array, VCI, starts at being 0. If I do RCO broadcast, I will do an RB broadcast, and I will increment the local value only. Notice there's a piggyback here. VC is on the message. And then I will do locally, I will deliver. So this I can always do. But then I will have RB delivers. And that's when things get interesting. Here I have RB delivers. So the message arrives here. It has the vector clock VCM on the piggybacking. Okay. So in fact, the way we're going to do this is that RB deliver, it's always going to put this in a data structure. It's going to hold it. So we have this pending set, and we're going to keep all this data that arrives in the pending set. And then we have this procedure that actually does the work of checking whether there's a gap. Okay? So this one is pretty easy. We put this data in the pending set, and then we call this procedure. So whenever there's an RB deliver, we check to see whether the gap has been closed. Okay? So the real work is done in deliver pending. Okay? Okay, put on hold. So here, you have to understand also the pseudocode. While there exists an element of pending, X, so this is like a record, contains an originating node, name of the node, a vector timestamp, and a message. While there's an element of pending, such that VCM less than or equal to VC. So VC is the local one. If VCM is less than or equal to VC, that means there's no gap. VC could be lower, but here it's grow, and it gets at least at the level of VCM. So this means there's no gap. Okay? So if there exists a message such that there is no gap, then we're allowed to deliver it, right? So if this condition is holding, then we're allowed to deliver it. So we deliver it. We do RCO deliver. We also remove it from the pending set, and we update, of course, the local vector clock. Okay? But it's not done yet. Maybe if we do this, maybe when you do this, it closes the gap for another message. So we have to check again. Maybe now there's another message that becomes deliverable. There could be many messages that are waiting, and we deliver one, then the next one becomes deliverable, and so on. There could be many of them. Huh? So that's why it has to be a while loop. There could be many of them. There could be many of them on hold, and they're in sequence. And when the first one arrives, then it can be delivered. The second one can be delivered. The third, the fourth, the fifth. Each time we deliver, we increase VC, and maybe it closes the gap again. So you see, VCM is the message timestamp, and VC is the local one, which is always growing. VC is always growing, and it's always making the gap smaller, this one. So when it goes at least to the level of VCM, then we can deliver. You see? So it's a little bit tricky, the condition. But if you look carefully, it's the correct condition. You should try running this algorithm by hand. Very important way to understand it. Try running it by hand. Okay? So that's it. That's all the code. No more code. So this is actually not so complicated, in some sense. But conceptually, it's doing a lot. I mean, in the number of lines of code, it's not so hard, right? You agree with me? It's actually conceptually doing straightforward thing if you understand a vector clock. But you have to understand vector clocks, otherwise there's no way you can understand what this thing is doing. It's all completely based on vector clocks. Okay? So that's it. That's the causal broadcast, the waiting version. So this one will be a little bit slower than the other one because messages in the previous one were delivered immediately when they got there. But here, sometimes they're put on hold. So if there's slow messages, they will slow everything down. If an early message is slow here and doesn't get delivered, then all the later messages get put on hold. Oh, that's a pain, So one slow message slows everything down, You can see that, Whereas the previous algorithm did not have the problem of slowing down. But the previous algorithm had another problem. Had this garbage collection problem, Had this growing message problem. So in practice, this one actually might be better, even though slow messages, if there's occasional slow messages, that will slow down this algorithm, You can see that, If M1 in the example is slow, very slow, then M2 has to wait until M1 arrives, okay? Whereas in the previous one, when M2 arrives, it already has M1 in the past list, so it immediately delivers M1 and M2. So the previous one is like optimized for the fastest messages, it's fastest, whereas this one is kind of pushing towards the slowest messages. What can you say? Maybe you can do half and half, maybe you can do maybe you can put some of the messages in the past list, and the other ones, you represent them as a number. So you can actually combine the two algorithms. You see how that could work? Where instead of putting 10 messages in the pass list, you only put 5, and the other 5 are just numbered as a vector clock. And that way, maybe you kind of get the best of both worlds, who knows? So then you can maybe tweak it. So you can see how you can play around with this kind of algorithms. Okay. So here, let me show you now another execution of this algorithm. So this one is a simple one with only 2 processes. Okay, so this one does a broadcast, and the local vector clock becomes 1, 0, and you have 0, 0, which is piggybacked, right? And now you do another broadcast on what's delivered up there. You do another broadcast here on P2, this vector clock becomes 0, 1. And now you have 0, 0, and 0, 0. So what happens here? You have 0, 1, and 0, 0. So basically, is there a gap? There's no gap, huh? Because this vector clock will only go higher and higher. So it's already at least at the level of 0, 0. Okay? It's at least at this level. That means when this message arrives, we can deliver it immediately. Okay? It's even gone a little bit higher because of this other broadcast. But that's not a problem. So we deliver it. So yeah, so first we deliver it locally. Okay? And then we deliver this one. We can deliver this one. Here we have 1, 0 and 0, 0. So there's no gap because this one has gone higher, higher. It's even a little bit higher than 0, 0. So at 0, 0 it would have already been okay to deliver it. But it's even a little higher, and that's not a problem. So we can deliver it. And then the vector clock becomes 1, 1. Okay? And the same happens here. So this message here, the 0, 1 is higher than 0, 0. So it's fine, there's no gap. We deliver and we increment the P1. So it becomes 1, 1 again. So both vector clocks are 1, 1. Okay. So that's an execution. But there's something strange about this execution. If you look at P1, M1 arrives before, is delivered before M2. If you look at P2, M2 is delivered before M1. So the delivery order is not the same. But we're in a causal broadcast, huh? So my question to you, what's going on here? What's wrong? Now I want to see if you're paying attention and thinking. What's wrong here? Remember, we're implementing causal broadcast, huh? The order is not the same. How's that possible?
Are different broadcasts.
Sorry?
Are two different broadcasts.
Yeah, so I'm broadcasting M1 and M2. Those are two different broadcasts. Yes?
So they are concurrent. They don't need to be...
They're concurrent, you say. Yes, these two broadcasts are concurrent. That's the answer. Thank you. So that means there's no order between them. The causal order does not define an order. That means they're free to arrive in any order they want. Okay? So what's wrong? Nothing is wrong here. Huh? Nothing is wrong. Okay? It's just that M1 and M2, those are concurrent broadcasts. There's no causal relation. So it's perfectly fine. Okay? See that? Notice I sometimes trick you. I try to trick you. Sometimes people don't get caught. But you see, this one is actually perfectly fine. You can see also these concurrent events, they cause the vector clock to increase a little bit more than what it should increase. But that's not a problem. It's allowed to increase a little bit more. There's no gap. So the concurrent events are not counted as in the gaps. Okay? Okay, so there you know. Now I want to make a summary of many different orders of broadcasts. So we saw already two. We saw, remember, in the very first course, we saw total order broadcast. We saw just now causal order. You can also define a simple version of that called FIFO order, or single source FIFO. So FIFO means first in, first out. Premier arrivé, premier parti. First in, first out. Okay, so let me define these. And for all of these, you can make broadcast algorithms. So the new one, which we didn't see before, is this single source FIFO order. So the messages from the same node are delivered in the order that they were sent. So that's a very simple one, because there's no transitivity. In causal order, you have this transitive rule, and that actually makes things complicated. But here, there's no transitive rule. You're just looking at the source and the destination only. For messages M1 and M2, and PI and PJ, if PI broadcasts M1 before M2, and if PJ delivers M1 and M2, then it will deliver M1 before M2. So the order is maintained between source and destination. So this is true for causality as well, but causality does more. Causality has this transitive rule, but here there's no transitive rule. Okay. Notice this condition is written in such a way that we don't assume the messages are actually delivered. That's part of the other broadcast properties. Okay? This property only assumes FIFO order for messages that are delivered. Okay? So that's a caveat. So that's something. This condition is like a minimal condition. Okay? Then there's total order. So we saw that already. Everybody delivers everything in exactly the same order. So for all messages, M1 and M2, and all PI and PJ, if both PI and PJ deliver both messages, then they deliver them in the same order. So all nodes, essentially, will deliver the messages that they deliver will be delivered in the same order. So again, this formulation does not require delivery. So it's a minimal formulation. Notice another thing. Everyone delivers in the same order, but it doesn't have to be the order that they were sent. If I send M1 and then M2, all the nodes could receive M2 before M1. The same order does not have to be the send order, the order of the sends. It only has to be the same. So that's total order. Okay, so you get it. You understand single source FIFO, you understand total order, you understand causal order. So now I want to do some exercises. Of course, I'm not going to show you simple, I'm going to show you kind of corner cases. Here I have two processes. A broadcasts here, B broadcasts. So these two are concurrent. The A is delivered here on P1, there on P2, and the B is delivered here on P2 and there on P1. So I have three questions now for you. Is this satisfy the property of single source FIFO? Yes or no? This formal property I just showed you, is it satisfied here? Single source FIFO. Yes?
No, it doesn't.
It doesn't. Why not?
A sends two messages from B, and it saves it. It also sends it to itself, but the order is not the same.
So what is single source FIFO? Please.
The messages should be received in the same order for A than they are.
If they come from the same process.
Yes. So
So where I don't see two messages coming from P1. You have to, the messages that are sent from one process, the same process will arrive. So so what did you say? Is this single source FIFO?
Can be.
It can be. So your answer is maybe. That's okay. It's better than no. I think the answer is actually yes. It's yes, but it's vacuous. We're not actually sending two messages from one node. There's an if. This is if then. So it's satisfied because there's no case that breaks it here. So yes. So what about totally ordered? Is this totally ordered?
No,
No. Why not?
because they are not received in the same order from A and B.
Yeah, so here we have A delivered first and then B and then A. So clearly they're not the same order, so it is not total order. Yes, that is correct. Okay. What about causally ordered? Okay. Is this a correct causal broadcast? Are the deliveries, is it causally ordered? Is it satisfying the causal property?
Yes.
Yes. Why?
Again, as before.
Sorry?
Again, as before, they are concurrent.
They are concurrent, which means that the causal order does not impose anything on them. So we're fine. We don't have to worry anything. Concurrent events, they escape from the clutches of causality. Yeah? So this is a causal order because the nice thing about causal order, or the funny thing, is that if the events are concurrent, then causality has no grip on them. Causality doesn't say anything about them. Huh? So that's the case here. Huh? Okay, things are not done yet, you guys. Here's another interesting one. Here we have A and B are both broadcast on P1. And here B is delivered and then A. And here B is delivered and then A. So is this a single source FIFO? No. Why not?
Because A is sent, then B, but we receive B, then A.
Ah, so here we do have two sends from the same process, huh? But A is sent before B. But the problem is B is delivered before A. So the order, it's not single source FIFO, but the reason is that the order is switched, huh?
But isn't like, yes.
Sorry?
Because here B is delivered first in both.
B is delivered first here, and B is delivered first there.
So it's FIFO.
Single source FIFO.
Okay, sorry.
Yeah, maybe later
Yeah.
you can say something, huh? Yeah. So this is not a single source FIFO. So is this a total order now? Is this a totally ordered broadcast?
Yeah.
Yes. Why? Why?
The thing is, because B and A are delivered in the same order.
Okay, but they are not delivered in the same order as they're sent.
Yeah.
Is that okay?
Yes.
That's okay, yeah, absolutely. So the total order only is talking about delivery order. Huh? So this is a totally ordered broadcast. Huh? Okay. Now, is it causally ordered? Again. So now we do have a causal connection between A and B. Yeah? I want an answer from this side now. Okay? Or from the back. I know these guys are paying attention very well. So, is this causally ordered? Yes or no? So this is actually asking something real because A and B, they are causally connected, huh? Clearly, huh? We don't have concurrent events here, huh? There is something going on here with respect to causality, yeah? Yeah?
So since we don't have concurrent events and we have A is before B,
Yeah?
we have that A is delivered after B, so causality is not preserved here.
Exactly. So
So
here,
yeah.
yes. So A is before B. That means the causal order means it has to be delivered before B2, but it's not. It's delivered after. So this is not a causal broadcast, huh? Okay? It's not. Okay? Okay, I'm not done yet, you guys, but this is the last one, okay? So here's another one. Here we have now a connection between two broadcasts. So A is broadcasting on P1, it delivers on P2, and after that, B broadcasts on P2. So is this a single source FIFO? That should be an easy question to answer, right? Right? Easy, and not you guys. You know the answer. Yeah?
Yes, because both messages don't come from the same source.
Exactly. So it's vacuous because A and B are not sent on the same. So we're not actually imposing anything here. So it's a single source FIFO. It's not a problem, huh? Okay. So what about totally ordered? Is this totally ordered or not? Somewhere in the back now. Yes.
No.
No? Why not?
Because A is received after B, and for the other one, A is received before.
Delivered, huh? So A is delivered here after B is delivered on P1, and on P2
A is before.
Delivered before B is delivered. So the order is not the same, huh? So it's clearly not a total order, huh? Okay. What about causal order now? Is this a causal order broadcast? Somewhere in the back here. Is this causal order? So, first of all, there is a causal connection between A and B. Huh? It's clear, huh? So the B is causally after A. Huh? A happened before B. That's clear. So, if you know that, what can you tell me about causal order? Is it causal broadcast or not? No? Why not?
Because A is delivered after B.
A is delivered after B, and A happens before B. So it's a contradiction. So this is not a causal order, huh? Okay? So you see how it works, huh? You see how the conditions work, huh, in these cases. So now, before the break, I'm going to summarize all of the broadcast algorithms we saw. So there's a lot of them, huh? So here's a 3x3 graph. So the simplest one is best effort. And then the most sophisticated one that we saw is uniform reliable causal broadcast, which is what we saw before, but on top of uniform reliable. Huh? And the arrows mean that it's strictly stronger. Okay? So if I have a best effort causal, it also satisfies best effort FIFO. If I have a best effort FIFO, it also does satisfies best effort. Huh? So we're just adding conditions. Huh? So we actually have not seen the code for all of these, but you should be able to write down code for all 9. It's terrible, huh? So many different broadcast algorithms. You never imagined there's so many of them. Because not all of them are useful. Now, FIFO is useful, and the reason is that it's very simple. It does not require any transitivity. It's only between source and destination, and sometimes that's enough. So FIFO is actually sometimes useful. Of course, causal is useful. That's when you have many nodes doing something where the causality between 2 random nodes is important, like a discussion, huh? Like a chat room. So causal is sometimes important. And sometimes you don't need anything. You just want messages to arrive. Huh? And you hope that the network makes it so that usually they arrive in the right order. So this is actually companies like Facebook, they're actually doing more like this, or even the email is like doing this. I have seen replies in my Mail Thunderbird client, replies arriving before the message I sent. Have you ever noticed that? You notice it sometimes. I guess it's because the clock of the other machine is not quite the same as my clock. So it's clearly not causal. Even a regular email is not causal, huh? It's a pain, huh? But yeah, that's life. So here you have all these algorithms. So the most complicated one is here, huh? Uniform reliable causal. If you're uniform, you're also reliable, huh? This is just an extra condition. This is an extra condition for failed nodes. But if you don't care about that, this uniform reliable is also reliable, huh? Okay? So you see that there's these strict, these are like problem reductions, huh? Strictly stronger. Now there's one guy that I have not mentioned here, which is total order. So my question now to you, notice this diagram here. Where does total order fit in this diagram? Where does it fit? How would you update this diagram and add total order in there? What do you think? Okay, you have to think out of the box a little bit here, because clearly total is not stronger or weaker than causal. The total order, the order is always the same, but it might not be the send order. So total, it could be total and not causal, but an algorithm could also be causal and not total. So there's no connection. Also, total order does not talk about the failed nodes. So total is orthogonal to this. So it's another axis coming out. So you could add the total condition to any of these. The total order condition, that all nodes receive in the same order. You can add that to any of these. So in fact, you double the number of algorithms. That makes 18 possible algorithms if you add also total order. And the most sophisticated one would be uniform, reliable, causal total order. That would be the most, in order to implement it, you could take our algorithm here, but you would need to add the total property. So I have not shown you the code for that, but one way to do that would be to use consensus, to make sure that the order is the same. So you would have to add another layer on top of this, if you want to make it total, or on top of any of them. You would have to add another layer on top that maintains that total order. But you can do it for any of them. So in fact, you have 18 possible broadcast algorithms, and you could write down the code for all of them, or you will be able to. It's amazing, huh? Of course, not all of them are as useful. Usually, many systems are going to be sitting here. Stupid, but sometimes that's not good. Banks, for example, they don't like this one. They need reliable, okay, and they also need causal. No, actually, they prefer total. If I do updates on a distributed database, and I have several copies, they must be done in the same order, clearly. Otherwise, the numbers in the accounts can be different. It's not always commutative. Okay? Okay, let me make a small break, and then we're done with causality, and after the break, I'll start talking about consensus. We'll faire un petit pause break. So now we're going to talk about consensus. So consensus is kind of the heart of the course. So now we've arrived at the heart. Consensus is probably, in current distributed systems, the most important algorithm in distributed systems to make them really work. So this is an important algorithm. If you've seen, I actually made some kind of an interview on internet. I think it's actually overused. I think you don't need to use it so much, but it is essential, okay? This is an algorithm that sometimes you absolutely need it. You cannot get around it. So it's very important to have it correct, okay? The idea is very simple. All the nodes propose a value, 5, 7, 10. They run the algorithm, and then there's a decision, and they agree on one of the proposed values. So the nodes agree. So agreeing between many nodes. This is a key thing, and some algorithms, some of them we mentioned, total order broadcast, you can implement it if you have consensus. It's also known as atomic broadcast, or atomic commit. So we mentioned already before, if you have distributed databases where all the copies have to do the same thing, it has to be consistent. It must be, like in a bank accounts, for example. You need it. Or even something subtle, like terminating reliable broadcast. Notice the reliable broadcast we saw, remember reliable broadcast? You run it, it's all or none. But none of the nodes actually knows when it's done. Now the nodes are running, but a node, if you ask the node, is the algorithm done or not? It doesn't know. If you want to add the ability of the nodes to know when the algorithm is done, that's actually hard. That's called the terminating reliable broadcast, and in order to do it, you need consensus. Okay, we're going to see that later. So many tools that you use, cloud tools, for example, orchestration tools, transactional databases, distributed on block managers, many of the large cloud tools in Google or wherever, Amazon, they are using consensus. They will not tell you how they do it, but they must use consensus to do what they can do. So one way I like to say it is that consensus can do heavy lifting. It's a very strong algorithm, and it can do many things. It's like a bodybuilder, okay? It can lift a lot of weight. So sometimes you need that, huh? Sometimes you need pure strength, and consensus is that. Okay, so that's just introducing. So what is it? So I told you all the nodes propose and then they decide. But we have to make very precise properties, huh? So we have 4 properties, okay? So all the nodes propose and then they decide. So any value decided is a value proposed. You can't have nodes proposing numbers from 1 to 10 and then deciding 300. It has to be one of the values proposed. That's called validity. It's a little bit like the network is not inventing things, huh? Okay, agreement, of course. That's what we want. No 2 correct nodes decide differently. That's the basic thing we want. Also, we want termination. Every correct node will eventually decide. It will just not run forever. And integrity, it only decides once, or at most once. Okay? It might fail, it might not decide, but it decides only once. Once it decides, it will never decide again. Okay? So each one of these is a very logical property, huh? Doesn't invent nodes, they agree, they terminate, and they only decide once. Okay? So that is the formal definition. So here's an example, execution. Okay? Nodes 1, 2, 3. This one proposes 0, proposes 1, proposes 0, and then they decide. Okay, this one decides 0, this one decides 1, and then it crashes, and this one decides 0. Okay? Does this execution satisfy the definition I gave you before? Let me show it very quickly again. See this definition? Does this execution satisfy that? What do you think? I'm hearing some vague, some sound floating in the air, but maybe it's not clear enough.
Yes.
Yes. Ah, that's clear. Why?
Because at the end of the algorithm, P2 is considered crashed, so
Yeah.
we don't bother with.
So it doesn't matter, because it's only the correct nodes that have to decide the same, huh? Okay? This is the regular consensus, huh? We will also have uniform consensus, huh? So here's another execution. So this one does, huh? Here's uniform. There is also a uniform version. So this concept of uniform is like a general thing, huh? It's when algorithms have to do something, they might fail or not. So the non-uniform one only worries about the nodes that don't fail. Whereas the uniform one, the node is allowed to do the thing and then fail. Okay? So remember we had uniform broadcast? Yeah? Question?
Yes, just about the previous slide.
Okay.
We considered termination because all nodes were crashed and the others had decided. Because, or do we consider only crash stop? Because if we don't have crash stop, if we have a crash recovery, for example, we consider the algorithm finished as soon as all actually non-crashed nodes have
Okay.
decided?
This one, so here we are worrying about crash stop, huh?
Okay.
So you're saying what happens if we have crash recovery,
Yes.
where it can crash and recover again? Then your specification has to say that. Huh? So a correct node is one that crashes and recovers. You consider that correct? Then this one it could crash and recover, and then it would be correct. And then this would not be a good execution. Huh? So this is for crash stop. Huh? You might have to slightly change if you have other crash models. Yeah?
On this slide, so what happens if P2 crashes after P1 decides 0? Does it still satisfy the consensus?
What happens if yes, because there is, if the crash is here, you're saying. Yes, because we're assuming that there is some point when the algorithm is finished.
So
Okay.
we look at the long term.
So we're not, this is not infinite. We're assuming that the algorithm is finished after some finite time, okay? So after this finite time, everything is done. So the crash is happening before then. It could be that P1 crashes here later on, huh? But we don't care about that because it's not. So every algorithm we run has some assumed termination, okay? Of course, things might change if the termination is at a different point, huh? But there is always an assumed termination for every distributed algorithm, okay? So when we run it, the termination is known by, the God's eye view, huh? The person who is looking at this space-time diagram will know when the algorithm terminates. But the nodes themselves inside the algorithm usually will not know that, okay? So that's kind of subtle. But we are always going to be looking at the algorithm from the outside, so we always know when the algorithm terminates. And when you build a system, you will always do that, okay? You will always know what is happening from the outside. You know more than the nodes. I know more in general. Of course, in any specific case, when I have a real running system, I cannot see. But I can reason about the whole system, okay? So this crash, as long as it happens before the assumed termination, then P2 has crashed, and the decision doesn't count, okay? So uniform consensus, the only difference is no two nodes decide differently. So nodes that crash are also allowed to decide. They might not, huh? But if a node decides and then crashes, it's part of this, huh? So no two nodes decide differently, not just correct nodes. So all nodes can decide. The correct nodes, they must decide, huh? The failed nodes, maybe they will decide. But if they do, they have to decide the same, okay? So in the uniform, a failed node that decided has to also decide the same. So that's an extra, a stronger condition, huh? So here's an example. So does this one satisfy uniform consensus? What do you think? Someone around here. Does this satisfy so uniform means, look at the failed nodes, huh? Does it satisfy uniform consensus? What do you think? There's only two possible answers. I can guarantee there's only two possible answers to this question. Yes or no?
No,
No. Why not?
because if we have in P1 decide 0 and in P2 decide 1,
Okay. P2 decides 1, yeah.
so the uniform agreement is not the same.
Okay. Because uniform agreement, it worries about all decisions even from nodes that crashed. Okay. So this is not a good uniform consensus. Okay. Even though it's a good regular consensus. Okay. So here's the interface. So you can see it's different from broadcast. Huh? You have a request and an indication. So here, all nodes propose, and then all nodes will eventually make an indication, which is a decision. And it's the four properties that are holding, yeah? Okay? So that's it. So it's actually a very straightforward algorithm, huh? It's not very complicated algorithm. But all the conditions are important, huh? Can't leave any out. And of course, there's always the question, which of these are safety and liveness? So I recommend you do exercise for that, huh? Some of them are safety, some are liveness. Okay. So now I'm going to show you an algorithm. So there's many algorithms for consensus. And this algorithm uses a perfect failure detector, but it's not absolutely necessary. You can make consensus with eventually perfect, and that's a major result of distributed systems, is how to do consensus on eventually perfect systems, okay? So this is a major thing, And the algorithm that was invented is called, the best one is called Paxos. There is a simpler version of that one called Raft that exists. And this one is the most powerful consensus algorithm. This was invented around 1990 by Leslie Lamport. And it was one of the major contributions in distributed systems, okay? But I will start by showing you this one, because the other one is more complicated, huh? This is hierarchical consensus. This one needs a perfect failure detector to do consensus, okay? And it also uses best effort broadcast. So again, it's layered on top of P and best effort broadcast, okay? So each node will have a local variable to store its proposal, and it can change the local variable. So it proposes, but maybe it changes the local variable, okay? So it has the local variable. The last adopted proposer is called last prop. You see there's some local variables to see what is the proposal and what is the node that made it. So the idea is this. So here's the basic idea of the algorithm. So it uses rounds, okay? You can do rounds because you have a perfect failure detector. So rounds means that all of the nodes start by doing round 1, okay? And then at some point, each node decides to go to round 2. And they're not actually synchronized, but because of the way the algorithm works, they will all at some point do round 2, and then they will do round 3 up to n. So that works because of the way the algorithm is written. So they don't have to actually do some complicated thing. They will go through all the rounds, and you'll see how it works. So in a round I, starting with 1, node I is the leader. So you start with round 1, and node 1 is the leader. The node 1 broadcasts its proposal, and it also decides on its proposal. So node 1 is like the boss, huh? And the other nodes, when they receive the message from node 1, they will adopt that proposal, okay? That's the one possibility. The other possibility is that node 1 crashes. So the other nodes, there's two possibilities. Either they get a message from node 1, or they detect a crash. Of course, they might do both, but there will always be at least one of those, and that's what we need. And that works because of the perfect failure detector. So each node has a clear message that arrives in the round. Either a message from node I or a detective crash of node I. You see, each node has a clear indication, a clear message that arrives in that round, and that will allow it to go to the next round, okay? And that works because of the perfect failure detector, okay? So that's important, okay? So the way it works is, of course, nodes can crash. We have crash stop. And the condition is there must be a first correct leader, because not all the nodes are going to crash. If we have n nodes crashing, there must be maximum n-1 crashes, so there will be at least one correct node, and we look at the earliest one. So the earliest correct leader, and all the nodes before that have crashed. Okay, that one, let's call it P, will decide and broadcast, and because it's correct, best effort broadcast will work right. And all correct nodes get V, they all adopt V, and future rounds after that will only propose V, because in that round, all the nodes will have gotten V, and because P is correct, the next nodes will never detect a crash of P, so the value will never change, okay? So the first correct leader is the one actually that decides, okay? So we need to do it like this, of course, because of crashes, huh? So if we do like this, it works. Okay? So here's kind of how it works. We have 3 processes, and they propose. I propose A, I propose B, I propose C. And now we have the 3 rounds. So I make this dotted line between the rounds, but it's not actually synchronized. But you'll see each node knows how to go from one round to the next. It will know when it's time to go to round 2. And you'll see how that works. So it starts by P1 proposing A, okay, or proposing A, okay, and it decides A. Very good. And it sends A, but let's say now that P1 crashes here, okay? So what happens to the messages? Well, it depends, right? Who is going to get these messages? Well, assume nobody gets the message. Okay? So nobody gets the message here. And P2 sees that P1 has crashed, so it moves to round 2. Okay? This moving is because it sees P1 has crashed. And in round 2, P2 is the boss. So P2 decides B and does a broadcast, okay? P3 also notices that P1 has crashed. P3 also moves to round 2, but P3 is not the boss in round 2, so P3 doesn't do anything there. It just moves to round 2. Okay? So that's what happens. So P2's message arrives here, okay, into P3. So P3 is now getting this message, and it changes its proposal to B, okay? And then P3 will move to round 3, okay? P2 will also move to round 3, and then everything will be done, okay? So that's how it works. But there's one problem that we have to solve now in this algorithm. So you see the idea is not so complicated, but there's one problem. This message A is traveling in the network. Okay, it's traveling, and somehow it's very slow, and it arrives here, out of thin air. So P3 is in round 2. P3 has already received this, and then it receives that. It receives, this is called an orphan message, and it's an orphan because the parent is dead, okay? P1 is no longer around, but the message is still there, so this is an orphan message. So the way to make this algorithm work is you have to take care of these orphan messages. And the basic idea is it's not allowed to break the algorithm, okay? So the only real trick about this algorithm is these orphan messages, that you somehow have to ignore them, okay? But in fact, it's not so hard to ignore them, okay? So you ignore the orphan message, and now P3, after it receives this, it goes to round 3. P2, after it does this, it goes to round 3. In round 3, P3 is the boss. But P3, oops. The problem is, if it takes this orphan message, it will decide A. Oops, that's not good, And this one has already decided B. So somehow we have to ignore this orphan, okay? That's really the trick. That's what we have to do, okay? We have to ignore the orphan. So we have some Boolean conditions. So actually that's not that, it's not so hard to ignore the orphan. We only adopt a message coming from node I if I is greater, if it's later than the previous one. So if an earlier message somehow survived and is coming in, last prop is equal to 2 here. 2 was the boss. But this one is coming from node 1. Okay? So this we make a Boolean condition. So we're not allowed to adopt this. So the trick in this algorithm is to ignore the orphan. But otherwise the algorithm is not so complicated. Okay? So that's the idea for the algorithm. okay? So the point is, the leader in some round might crash, but much later, it might affect a node in a greater round greater than R, because of an old orphan message traveling that arrives, okay? So the way to get around that is to order all the nodes. P1 greater than P2 greater than P3. So we only adopt if it's lower. So we never adopt from the higher ones because we know they've crashed, okay? We only adopt if the proposer is lower than the last one that we've accepted. Lower, because the previous ones have crashed. Otherwise, P has crashed and should be ignored. So that's really the only trick in this algorithm, okay? So here's an execution without failure. So the algorithm will always do all rounds. 1, 2, 3 here. And processes and rounds. So if P1 proposes A, decides A, sends A, 2 and 3 will both receive the A, okay? And when they receive the A, they will update their proposal to A. The last proposer will be 1, 1, okay? And then they go to the next round. So this, after this broadcast, P1 goes to round 2. After P2 receives a message, it goes to round 2. P3 goes to round 2. And then in round 2, P2 is the boss. So it decides A. Okay, but it's the same as before, nothing changes, huh? So this decides A, this decides A. And the third one, well, in the third round, it will also decide A. You see, so everybody decides A. But everyone, each node only decides in the round where it's the boss. Okay? So that's the execution when there is no failure. Yeah?
Why do we change rounds? Why do we switch from round 1 to round 2? If there is no
It's
failure?
because of crash nodes. Each node has to have the chance to be the boss. So what happens if a node crashes?
Yes, but if there is no crash,
If there's no crash,
why should we?
because we don't know that beforehand. We don't know. I mean, yeah, in this case there's no crashes, but when you start running the algorithm, you don't know that. It has to work when there's crashes.
Yes.
So this is how, the algorithm works with no crashes. With crashes, this is how it looks. It has to go always through all rounds. Yeah, so this algorithm always goes through all rounds, and this one you can prove it works when there are crashes. Because there's always going to be an earliest node that is correct, and the previous ones have crashed. So each node has a chance to be the boss. But if P1 crashes, then P2 will be the boss, and P2 will decide. If P2 and P1 crash, then P3 will be the boss. So no matter who is crashing, some node will be the boss. Okay? So in this algorithm, the way that's done is by sequentially going through the rounds. You could do other algorithms, but in this algorithm, the way you let each node have a chance to be the boss. Okay? And the first node that does not crash will be the one that actually gives the value, the right value. Yeah, so that's the reason why you have to go through all the rounds. It's because the node might crash. It might, okay? So P1 might crash here, we don't know that, okay? But if it does crash here, then eventually, because of the perfect failure detector, P2 will know that, and P2 then will make its own decision, and be the boss. So this algorithm, it looks weird, but the reason why it has to go all through those rounds is because of the crashes, yeah?
We cannot know earlier which node will crash.
I'm not sure I understand. A node can crash at any time. when the algorithm is running. Any node can crash at any time, and it always has to work. So what scenario are you thinking about?
Is it possible that message from A is delivered after the message from B to C? And then what do we do? Or
So the message from A, so what scenario we're talking about?
it's delivered after the proposal of B.
So this one is delivered when?
After. But then we don't care because it's the same.
If the message is delivered in a later round, then it would be ignored. Because of the round numbers, because of the numbering, okay? Whenever a node receives a message, it goes to the next round. So this one receives a message, it goes to round 2. It receives a message, it goes to round 3.
So the rounds are not fixed in a certain time, but it's when
They're like, yeah, these times are not exactly the same. Huh? Each node changes round when it receives a message from the previous node. Okay? So P3 will change round when it receives the message here. But what if P1 crashes? Well, then P3 will receive the crash message because of the perfect failure detector, and then it will also go to the next round. So you see why it's important to have a perfect failure detector. Huh? If we didn't have that, this wouldn't work. Yeah? So P3 always knows when it has to go to the next round. Huh? So, but these times are not exactly the same, of course, for all the nodes. It's logical time. Huh? Each node will sequence 1, 2, 3, but it might not be exactly at the same time, of course. Huh? This message might be slow, this one might be fast. Okay? But it's true that this one sends a message. This message might be coming later. But the only way that will work is if P1 crashes. And then this one has already gone to the next round, and then this is an orphan message that we can ignore. So you see, it's a little bit tricky, yeah? Yeah?
Is it possible that a node switches from round 1 to round 3, for example, without...
No. It will always go to the sequential, in the road, the nodes will never skip rounds. So P3, it starts in round 1, and it will always go to round 2, and there's 2 possibilities. Either it gets a message from P1, or it gets a crash from P1, from the failure detector, crash P1, and then it switches. And it always goes to round 2. The rounds are never skipped. And that's important because any one of them can fail at any time. So we always have to have this complete diagram. Huh? Because P1 can fail any time here. P2 could fail any time. And it always has to work. So the nodes are not allowed to skip anything. You have, all the nodes have to go through all the rounds. Okay? So here is an execution with a failure. So P1 now decides and then fails. Okay. P3, let's say it receives the message A. Okay. But P2 will also go to round 2. Okay. So P2 will get the crash message from the failure detector. But P3 will get the actual message from P1, okay? P2 will decide B, okay? Like that, decides B, and we're assuming this one is not arriving, but if this one does arrive somewhere, then it's an orphan message, huh? And this one is coming from P1, and if we're in round 2, then the last prop will always be equal to 2. Huh? So you can reject it. Huh? Okay, so that's regular consensus. Okay, just a little bit more before we stop for today. How do we make it uniform? So remember, each node, we go rounds 1 through n, and each node is the boss in its own round. So here's an example execution, huh? So you notice that P2 decides B, P3 decides B, P1 decides A, and then it crashes. So is this uniform? Is this a correct uniform algorithm? What do you think?
No, because they didn't choose the same.
No, because, yes, because P1 decides and then crashes. So uniform, we have to worry about this one too. So this one, in the algorithm I just showed you, the P1 decides and then crashes, and then the others decide later. So each one will only decide in its round, okay? So P1 decides in round 1, and then crashes. P2 decides in round 2, P3 decides in round 3. So that's fine for regular consensus, but it's not uniform. So what's the problem here? The problem is that somehow the decisions are being done too fast. Remember, in order for something to be uniform, you have to be very careful. If I decide and then fail, if I decide and fail, I'm not sure the other guys have received A, so I don't know whether they can decide A. It's like for uniform broadcast, If I do a broadcast, if I deliver and then fail, I have no idea whether the others are delivering, So I can only decide when I'm sure that everyone else will decide the same thing. Okay? So the trick is to delay the decisions. It's like for the broadcast. You have to be very careful when you decide. Okay? So here, the problem is you're deciding too quickly. So you're not uniform. Okay, so this is not uniform. So we're going to do a uniform one, but we'll do that later. So you see, this one is not uniform, because we're deciding too quickly. We're deciding in the round. So in the uniform one, we're going to have to decide later. Okay, but I won't show that one today. Let me just show you the hierarchical one, the rounds. So the trick is you go from one round to the next. Okay, so it's 2 pages of code. So it's not that much. We've already seen algorithms with 2 pages, So we have a best effort broadcast and a perfect failure detector. We have some local variables. We have the round number here. We have the proposal. So this symbol means that there's no proposal. You can read it bottom. It means no proposal yet. Last prop is the last proposer. Okay. And then we have some variables, some Boolean variables. So we'll see. So here, for example, we have a crash message. And we have this detected. So these are the detected crashes. This will tell me the processes that have crashed. Okay? So all of this is initialization. So the real code of the algorithm is here. So this is the whole algorithm. Okay? So a lot of these things are simple. So we'll go through the simple ones. So every node I proposes. So I have a propose request. Okay? If the proposal is bottom, then I send it to V. Okay? Why do I check this? Because initialize, it's initialized to bottom. Well, because it's a concurrent thing. So when I do propose, maybe some of the rest of the system is already running. Okay? So maybe there's already a value there. Okay? So it only gives the value if there's no value before. Okay? So that's this one. Okay? Then we have some work, and then we have some going to the next round. Okay, so here is when I'm the boss. Round is equal to the rank of me, of self. That means I am the boss. So in round 1, this will be P1, round 2, P1, P2. So this variable round is equal to the rank of the process. Huh? So P1, P2, P3, that's 1, 2, 3. So P1 has rank 1, P2 has rank 2, and so on. And this Boolean here, broadcast round is false because you're only allowed to broadcast once. Okay, it's like the delivered. I set it to true, so I'm only broadcasting once. And I only broadcast if the proposal is not bottom, if there is a proposal. Okay? So this is just the broadcast when I'm the boss. So I decide, of course, and I broadcast, and that's it. Okay? And then here is when it's delivered. So P1 is the boss, it broadcasts. P2 gets the message, BEB deliver, and it sets its local variable. Proposal gets V, and last proposer is R, which is the last proposer. And then there's this condition here. If R is greater than last prop. What does this condition do? It's the thing I showed a few minutes ago. Why do we have this condition? Why don't we just always set the proposer to V? Because?
Orphans.
Because of orphans. Because this might be an old message coming from an old round. So the round might be low numbered, old one. So only if it's a newer one, greater than last proposer, then you do it. So this ignores the orphans, Okay? Here, and here we have the trick for going to the next round. Okay? So how do we go to the next round? Well, there's two conditions. Either round is detected, so that's actually the crash. Remember in the previous code, the previous thing here? When there's a crash, I add the rank to detected. So either I detect it's crashed or delivered. The message delivered, that's why I set this delivered flag to true. This lets me detect that I actually got a message in that round. So in round, I got a message, or the boss of that round is crashed. And then I increment the round. So this is how to go to the next round. So you see, these are all very simple things. But together, it makes the whole thing go from 1 to n, and each proposer decides when it's the boss. So this will implement the consensus. So it starts by setting the initial proposal. So here, if I am leader, I only trigger once per round, because otherwise it wouldn't be good. I have a Boolean that makes sure I only do it once, and only if I have a proposal. I actually decide permanently. So when I'm the boss, I permanently decide, and that will be the decision unless I crash. And then I do a BEB broadcast. So here I'm only adopting newer ones. So the old ones come from orphan messages, so I don't adopt them. From previous rounds, I don't adopt them. And here I go to the next round if I either got the message, so deliver, or I detect the crash. Okay? And that's it. So that's a simple, well, it's not actually such a simple algorithm. You can agree that the code looks simple, but it's actually kind of a subtle algorithm. Okay, so let me stop here. Let me not try to prove the correctness, because I think your brains are full now for one day. And so next time we'll go back and I will recapitulate a bit of this so that I get a good intuition on it. Okay. So, and we'll talk about eventually P also next week. We're going to talk about, so next week is actually an important lecture because it's where we start really getting serious about consensus. Huh? This is actually a simple consensus because you have a perfect failure detector here. Okay? So this one will actually not work on internet. This is not the one that Google uses. Next week we'll talk about the ones that are used by companies, eventually people.